Okay, in this video, we're going to learn how to work out a class example using ANSYS Workbench and one-dimensional beam element. So we're looking at a part made of two rods, AB and BC, fixed at A, and at C it is free, but there is a wall at a distance of 0.002 inches away from C. This is made of a material that has a modulus of elasticity of 10 times 10 to the power 6 psi. The area of AB is 1 square inch, area of BC is 1.5 square inch. So we can use that to find the radius of AB in inches, and the area of, and the radius of BC in inches. When we are looking to model that to find the wall reaction and the internal forces in the parts and the displacement of B. When we examine the behavior of this part, we can quickly realize that it's going to be either in tension or compression because all the forces are acting along the axis of the part. And this is really important to understand how a part is going to behave to make sure that you are picking or selecting the correct element type. So for this type of a problem, we're going to be using a bar element. But I have to check the ANSYS beam element library. The ANSYS element library. And within ANSYS element library, we have an element known as a beam element. And this is capable of capturing the behavior of a bar or a beam or a frame or a shaft. So it can handle axial load, transverse load, bending moments, as well as torques applied to a one-dimensional element. So this element is very well suited for this type of problem. And when I model this using one-dimensional element, I'm going to need to create a very simple geometry. My parts are going to be made out of lines. So I'm going to have here AB 10 inches long, BC 12 inches long, all oriented along the x-axis. Anytime I'm working in ANSYS Workbench, I'm working in 3D. So even though this is one-dimensional problem, but I'm going to have an X, Y, and a Z direction that I'm going to have to keep into consideration. So when working in 3D, I'm going to have a third dimension here, which is Z. This is why when defining my geometry, if I'm going to be inputting points A, B, and C using ordinates, I'm going to need the X and Y and Z coordinates of each point. So if I place A at the origin of my coordinates, then its coordinates are going to be simply 3 zeros. As I move to point B, only X is going to change and it's going to become 10, and C is going to be 22. So I have a point C at 22 inches, 0 and 0. So this is my model, discretized model that we're going to be doing. Really, if I'm doing this by hand, 2 elements are sufficient. But as we're going to see within ANSYS Workbench, because ANSYS meshes without realizing how this part is being loaded, is going to create multiple elements within AB and within BC. When we were working this by hand, we wanted to have fewer elements because we were doing all the computation and matrices. Within ANSYS, ANSYS is going to be doing the work in the background, and as you can see, it's not going to take a minute to complete the solution. So we are depending completely on the computation ability of our computer. So let me switch to ANSYS and see how we're going to solve this problem. So within ANSYS, I launch ANSYS Workbench, and I'm looking here at a blank project. I'm going to start by saving this project, save as, and I'm going to give the project a name. I'm going to call it class example. So I'm going to pick my directory. I'm just going to put this on my desktop, and I'm going to call it class example. So it is saving the project. And if I open Explorer and go to desktop, you're going to see here that I created a file called class example. And this file has an extension WBPJ. Stands for Workbench Project File. Simultaneously, you can see that I have a directory or a folder also called class example. And this is something important for us to know, because the file, the WPBJ file, is going to have multiple links to several other files that are saved within that folder. So if I share with you my WBPJ, it doesn't mean that you have everything. You can't really do anything with it. And this is another important thing that I want you to learn to do. If we are to share files, I have to create an archive that I can share if I want to share one file. And you can do that from file. You can go and choose archive. And I'm going to leave the name as class example. And if you look carefully here, the file type is going to save an archive file. It's going to have an extension WBPZ for Workbench archived file or zipped file. So if I save this archive and go check my directory, oh, I think I saved it in the wrong place. So file, archive, I want to make sure its desktop is selected so we can see it. Desktop, save. I think now we're going to see it. Okay, so now we have two class example files. One is WBPJ and one is WBPZ. Okay, next, I'm going to start by creating an analysis system, namely a static structure. So I'm just going to double click. And here are my 7 steps. The first one is to define the analysis type. So I have a static structure analysis system. Within that system, I need to make sure my material is defined. So I'm going to go to engineering data and double click engineering data. And I do have a default material of structure steel. That's not what we want. So I want to create my material. So I'm going to click add new material, and I'm going to call the material class example material. And I'm going to click enter. And we are working with a linear elastic isotropic elasticity. So from the toolbox, I'm going to double click isotropic elasticity. And I need to define my modulus of elasticity, which is 1e to the 7 for 10 million. And one thing you would notice, the units. I am inputting the units, and this is my responsibility to select the correct type of units. Our problem is in US customer units, and by default, ANSYS picked SI units. So before I move any forward, we need to learn how to fix that. So I'm going to go to units, and I'm going to change the units from metric. I'm going to change that to US engineering units, where I can see inches and pounds. I'm going to go back to units, and I want to make sure that display values are in the project units. Okay. Now, I look at my number that I input here, that was Pascal, was converted to PSI. So I want to come back and fix that. And this really should be 1e to the 7 for 10 million. So now we have 10 million PSI. You see that Poisson's ratio is highlighted because ANSYS does not realize that we are working a 1D problem, but I could be looking for lateral strains as well. So we're going to have to input a Poisson's ratio. As we have learned, most metals have a Poisson's ratio about a 0.3. So if Poisson's ratio is not given, I'm going to use a 0.3. Oops. So here is my material. This is enough for what we need. I'm going to toggle back to project. I'm going to move to the next step with geometry. Please be careful here. You want to right click, not click the left button of the mouse. And we are going to choose to create a new design modeler geometry. So I'm going to click that. And this will launch our second platform, which is Design Modeler. So it says here, starting Design Modeler. Here comes a Design Modeler. Very typical to a CAD package. Again, we have the pull-down menus, toolbar. We have a graphics big area. And to the left, I have a tree outline. And then under that, you're going to notice that in Design Modeler, we're going to be working on one of two modes, either modeling or sketching. For this example, we're not going to need to do any sketching. We're primarily going to be working in modeling. And under that, there is a detail view. So if we need to define any details, we're going to be able to see them here. By default, we have the default planes X, Y, ZX, and YZ. You can see that under the tree outline. If you look on the graphics window, we cannot see these default planes, but I can turn them on and off from the toolbar menu. So if I come here, display planes, now we can see our planes. We can also see our coordinates, X, Y, and Z. And yes, for this problem, everything is going to be along the X direction. So if I want to be looking at the XY plane, I can come here and select the Z axis. So now I'm looking at the XY plane. Next thing I want you to pay attention to, the ruler. If you look at this ruler, you see that the units for the geometry we're going to be created is meters. So again, this by default is going to SI units. So I want to go to units and make sure to change that to inch. So this here changed. Now we're going to be working to the right of the y-axis. And I'm going to have a 22-inch long piece. I want to make sure that I can accommodate that. And next, we're going to start creating points. So I'm going to go to Create, and I'm going to select a point. You see the yellow flash icon? This is work in progress. And you see under modeling, there is a detailed view of point 1. right? And of course, this point 1 is going to be representing my A point, so I can change the point name from the detail view. And the type, this is a construction point, and then you have a definition. And for the definition, it says from coordinate file. My input is much simpler than that, so I'm going to change that to manual input. When I say manual input, it's going to be expecting me to input the coordinates X, Y, and Z. And per our problem, we were looking at 3 points. Point A is all zeros at the origin. Point B is going to have a 10, and point C is going to have a 22. So this is good for point A. The point has not yet been generated, so I need to click generate. You see the icon change from the yellow flash icon to the green, and I do have a point on the graphics coinciding with the origin. I'm going to repeat the same process 2 times so you can follow along. I'm going to create point B. So we're going to go do another point. Here it comes. I'm going to change the name to B. I'm going to change the definition to manual input. And now I'm going to put an X coordinate of 10 inches, enter, and then I can click generate, or I can click F5. Okay. Here comes point B. Next, we are going to create our last point, and I'm going to call this point C. And we're going to change the definition to manual input. And I'm going to change the X coordinate to 22. Again, you see the yellow flash icon. So I have to generate in order, click generate for the point to come. So here are my 3 points within my graphics area. Next, we want to connect these points with a modeling feature known as a line concept. And it is important to use the line concept because when we go to mechanical, ANSYS is going to realize that we need to use beam elements for these line concepts. So if you go to a concept in the menu here, there is line from points. And that's what we're going to be using. So I'm going to go and create a line from point. And we're going to create 2 of them. The first one is going to be for AB under modeling. And we need to select point segments. If you read here, it says line from point creation, select pairs of 2D points or 3D vertices for this feature. So we're going to be selecting 2 points. So I'm going to come here and I'm using my selector. I'm going to click point A. And then I'm going to use the control key to select my second point, point B. So I'm clicking control and do a left mouse select. You're going to start by seeing a green line to make sure that this is where we want to create that line concept. If we like it, we're going to click apply. The color changed to light blue, but the line is not yet generated. So we have AB, but you still see the flash icon. It will be generated and the color would change to dark blue when I click generate, or actually gray. So now I have a check mark next to AB, and AB line concept has been created. If you're paying attention, before creating AB, I had 0 parts, 0 bodies. Now I have 1 part and 1 body, and this body is this line body. I'm gonna do the same to create BC. So I'm gonna go to concept. I'm going to repeat the exact same steps so you can follow with me again. Lines from points. Here comes line 2. I'm going to change its name to BC. Then I'm going to go to point segments. Again, I'm going to have to select my first point, press the control key, and select point C. So this connects between point B and point C. Before I click apply, I want you to pay attention to another thing here, the operation in the detail view. It says add material. So we're adding material to build our model. But one thing we want to notice that AB is going to have a different cross section than BC. If I continue to use add material, I'm going to end up with one line body that can only take one section. So it's not going to allow me to apply different sections or assign different sections to these bodies. So at this point, I'm going to have to change add material to add frozen, which is going to create two parts, two bodies and two parts, two distinct parts. We don't want to leave them distinct. So let's take it one step at a time. Let me accept that by clicking generate to generate this BC. So when I click generate, I ended up here with two parts and two bodies, two distinct line bodies and two distinct parts. If I also leave them like that, meaning I'm going to have two parts that could be separated, they're not welded together, right? So we want to make sure that before we get out of Design Modeler, that we form a new part. But let me first show you why we needed these to be two distinct lines. Because if you select any of these bodies, you see that there is a highlighted, under the detail view, the detailed section is highlighted. ANSYS knows that we don't really have any parts that are simply lines. So there must be a cross section that need to be assigned to that line concept. So first, if I go try to assign anything, I don't really have any sections yet defined. So I'm going to need to define my section. So I'm going to go to concept again, and all the way down in the pull down menu, there are cross section. And you see there is a good list of standard sections, or you can have your user defined section. For this example, we are working with a circular section, which is very easy to define. So if I click circular, it's going to show me like a sketch, but I'm not really in sketching mode. All what is expecting from me is to define the radius, So when we look at the problem here that we are working on, the radius for AB is 0.56419. So I can come here and change the radius from 1, the default, to 0.56419 inches. So that's the radius of a circular section, and I can come here and call it circular section for AB. So that's circular AB. I'm going to define another circular section. So I'm going to repeat concept, cross-section, circular. And here I have circular 2, or I can change the name to BC. And I'm going to input a radius of 0.690988. These are calculated for a 1 square inch and 1.5 square inch respectively for these sections. All right. So I got here my two sections. So I'm able to go back to line body AB, the one that is highlighted, and assign now circular AB. Likewise, I can go to BC and it's the line body, and I can assign circular BC. If I want to confirm that I did that correct, I can go to the view and do like something like rendering. This is still one-dimensional geometry, but I can come here and turn on cross sections and look at this. I can see the smaller diameter of AB followed by BC. Please be reminded, this is not 3D geometry. This is still 1D geometry, but I am showing the cross section. If I even rotate it, you can see the circular sections, right? So I'm going to turn this off again from view. I'm going to turn this off so we remember that we are working with one-dimensional elements. We're not going to stop here, but the last thing we want to do is to make sure I form one part out of these two parts. How we're going to do that? We're going to be using the tree. I'm going to select the first line body and then Control key, the second line body. So now I have two of them selected. I'm going to do a right click. And if I go down here, it says form a new part. I'm going to click to form a new part. And now look at the tree outline. It says I have one part made out of two bodies. Okay. So this completes the geometry definition. So now my geometry is done. I can come and double click on model to launch ANSYS Mechanical. So it is starting mechanical. Here comes ANSYS Mechanical, and we should see the geometry and the material, the geometry that we create in Design Modeler and the material that we defined in Workbench. And please remember, the first step we want to do, here comes my geometry. I want to make sure that my geometry, which is the part, has the correct material assigned to it. So by default, it got the structure steel. So I want to come here, select the structure steel. You see the arrow. So I have here like a menu, and I see the class example material that we defined. That's the one that needs to be assigned to my part. And I assign it to the part which really is composed of the two bodies. So I select here class example material. Before I move any forward, let's check the units. It is our responsibility to make sure that our units are consistent. So I go to home and I go to units, and I have here US customary units selected. So we are good. You look at the ruler, it's in inches, looks good to me. Again, we're going to be working along the x-axis. I'm going to select the Z. So now I'm looking to the XY plane. If we go to our steps, we are going to be working on the model. We assign the material. Next, we need to generate the mesh. So I'm going to come here and go to mesh. And if I select from context the mesh menu, you see there is an icon that says generate the mesh if out of date, or if I'm just creating the mesh for the first time. So I can come here and click generate mesh, and now it is meshing and 100% done. And look at this. This is what my mesh is going to look like. So what happened here is ANSYS inserted about 21 elements when really 2 were sufficient. So basically, I have a finer mesh than what I need. which is okay. We're going to accept that. We're going to take the default mesh that ANSYS provided. Later on, we can learn about refining the mesh or changing the element sizing. So I'm done with my mesh. My next step is going to be, I'm going to go to static structure to define my constraints and my loads. So I select static structure from the project outline. And you can see here in the toolbar menu, I have different types of supports. We know that our part is fixed at A, so I'm going to pick a fixed support. I'm going to come, and please be careful when you're using the auto select. You see this here is a smart select. You can select a vertex, an edge, or a face. I want to make sure that I'm selecting the vertex, which is point A, and not accidentally pick AB. So I'm going to come here and select point A and apply. So this is a fixed support applied to point A. Now at C, we do not have a fixed support, but we know that point C, as a result of the loads and the test that we've done, that it's going to get a displacement, is going to move all the way to the right until it hits the wall. So if I look at the problem we are trying to solve, and when we checked how much AB is going to elongate, AB can elongate more than the 0.002 inch. So point C is hitting the wall. So we know the displacement of point C. So this is a prescribed displacement. So I'm going to come here from the support types. I'm going to pick a displacement. I'm going to select point C, and I'm going to say apply. So that's the geometry. And you see here the displacement components. Point C is only going to displace in the X direction, and it's going to displace 0.002 inches. So this is in inches. So these are the two boundary conditions that we needed to define. Next is we want to apply a force at point B. So you look here at the toolbar menu. I'm going to select a force. And here is the detailed force description. And it's expect me to select the geometry. I want to make sure to select point B. So I'm going to select point B and go apply. For the definition of a force, the default is to define the force as a vector. But for a problem like this, it's really easy to use components. So I'm going to select components. And I have a 10,000 pound force in the X direction. So I'm going to put here my 10,000 pound force. This takes care of supports and loads. If I want to check what I've done, I'm going to go to static structure. It's going to show me A, B, and C. I have two boundary conditions and one load applied. Now we're ready to check if there is a solution to this problem. So if I go to solution, and this is the easiest step if you have a good model. If you do not have a good model, the run is going to fail. So you see here I have a yellow icon, flash icon. If everything is good, it should be turned to a green check mark. So I'm going to click solve. And now it is creating a solver input, 10%, building mathematical model, putting all the equations together for 21 elements, right? All the matrices. This shouldn't take a minute. 50% solving the mathematical model, 85% solving, and we're done. We got a green check mark, and we can look at a solution information. But this is not really the results. If you really want to dig into some of the things that happening, type of elements, number of beams, you can read this lengthy file. But that's not what we want to look at this point. What I really want to look at is the results. I want to see what this is doing. First thing, before I start looking at numbers, I want to look at the behavior. So I always like to check the deformation. So I'm going to go to deformation and just simply pick total deformation. And I want to see if this part is doing what I expect. Under solution, I defined a total deformation. I'm going to solve for that. And let's look and see what we get. So we get this fringe plot showing us the deformation. And yes, I get a 0 where it's fixed. I get a 0.002 at C, and I get a higher number at B. And if you look carefully, if I go use a probe around that B point, we are getting this maximum of 0.00555, which you may recall when we did this example using the classical method and matrices, that's the number we got. But I really want to show you something cool. If I click at that play button, this will show you kind of an animation of what's happening. So AB is stretching and BC is getting compressed. We're going to see that more when we start looking at the internal forces. So I'm going to go to solutions again. And some of the things we wanted to find were the wall reactions, displacement at B, and the forces within the member. So in the next few minutes, I'm going to show you these quickly. So from solution, we see here in the toolbar menu, there is something called a probe. Like we use probes in the lab, we can use the probe here. I go probe and I want to define a force reaction. And when you're defining that, the boundary condition is what I'm using to locate the reaction. So I pick fixed support, that would be the reaction at A. I'm going to create another probe for another force reaction, and I'm going to pick the displacement boundary condition, which is the reaction at C. I'm going to do a third probe for a deformation. So I'm going to come here and look at deformation, and geometry selecting, I'm going to pick point B. Please make sure you're picking a point, not a line. And I'm going to go and say apply. When I'm looking at deformation, I can be looking at the total deformation or the deformation in the x-axis, right? In this case, the total deformation is the x-axis, but if you do the total, you're not going to see a sign because it's simply a magnitude. So I'm going to select the x-axis. And of course, we expect it to be positive, right? So let's look at these three first. I'm going to click solve again, and let's look at the force reaction. Here is my reaction at A going to the left, and you look at the number 5,554. When we did this using the analytical method, we got 5,555. So is there a numerical error? Yes, it's a numerical method, but the error is way smaller than even 1%. So this is very acceptable. Let's look at the reaction at point C at the wall. And I'm getting here 4,445 pounds. When we did it analytically, we got 4,444. Again, the error is very small. Deformation probe to look at the deformation. And at point B, I'm getting a 0.00559 inches. When we did it analytically, we got 0.00556. So there is again a small error here, but it is very acceptable. The last thing I want to do quickly is to show you how we can look at the internal forces, and this is only there because I'm looking at beam elements. So if you go under beam results, choose axial forces, right? And without doing anything else, if I click solve, that's going to show me the normal forces within the parts AB and BC. You see AB is in red, meaning it's in tension, and BC is in the dark blue. And when you look at the fringe plot, dark blue is a minus 445, meaning it's, 4,445, meaning it's in compression. AB is in tension 5,554 pounds. So with that, we are able to complete the solution for the problem that we did analytically and using matrices, and showed that we're able to get the same results using ANSYS mechanical.